In this video, we'll cover line beams and band beams in the SLB software. Specifically, what will be covered is we'll discuss what is a line beam, what is a band beam, how we define them in the software and edit their properties, what settings affect the beam design, and then how we view the beam design results. What we mean when we say band beams and line beams. So a line beam is just your typical traditional beam that has a depth greater than its width. So it acts predominantly in one direction, so one-way bending and one-way shear, and it's covered by Section 8 of AS 3600. A band beam is a beam that has a width much greater than its depth. So it exhibits behavior of both a slab, a two-way slab, and a beam, so basically one-way action. So this could be designed to Section 8 and or Section 9 of AS 3600. Now, there's no guidance in the code as to when we design it as a beam, when we design it as a slab. Do we design it to both? Are we being too conservative? So again, we'll touch upon it in this video, but that will be covered in more detail in the next video. So line beams, or these conventional one-way beams as they appear in the software. They're drawn by pressing the beam button in the Home tab, and we press twice, once to define the start point, once to define the end point of the beam. What is happening internally in the software when we draw a line beam is that we apply a line of stiffness to each of the finite element nodes along the beam center lines. This stiffness is related to the properties of the beam that we define, so the width, the depth, the concrete grade, all the other design parameters. So in this case, we're going to be applying a line of stiffness to this slab zone along nodes 1 through to 9. Band beams and wide beams are a little bit different. How we define a band beam, we just define it as a thickened slab zone. So as mentioned in the previous video, to define a thickened slab zone, we draw an area using geometry lines, mesh, and then apply a different thickness. So in this case, to define the width, we have to draw two geometry lines along the length of the beam, mesh, and then input this increased thickness of 400 millimeters. So this is the structure within the software. When the program is run, it doesn't know that this is a beam. It just treats it as a slab zone, so as a two-way plate, acting in two directions with capacity in two directions. The program doesn't know to design it as a beam until we draw a wide beam over the top of it. What a wide beam is it's simply an integration tool that we use to extract forces from an area and then design that area as a beam. So again, repeating one more time, the band beam is simply the structure, the thickened slab zone, and the wide beam is an integration tool that we use to extract the forces from a thickened slab zone, or any slab zone for that matter. Now we'll have a look at how we draw band beams, wide beams, and line beams within the software. We'll start with the line beam, as it's the simplest, and we draw it by pressing the beam button in the Home tab or using the shortcut B. We click once in the working area to define its start point and a second time to define its end point, and I'm just using snap to grid here. So hitting escape and selecting the beam, we can see its properties on the right. We can see the coordinates of its start and end points, which we can modify manually here as well. We can drag the beam, we can drag its ends if we want to move it to a different location. And we can start modifying its width. So notice as we modify its width, the shrinkage and creep coefficients are changed automatically. Because this is the default setting, the program automatically calculates creep and shrinkage based on the section properties that we've input. As mentioned previously, the line beam is simply a line of stiffness that's applied to the mesh along its center line. So if we hit F5 to mesh, we can see that basically we draw on the beam along the slab edge, so a line of stiffness will be applied to these nodes. Note that visually we see half of the width hanging over the edge of the slab. Again, this is purely visual, it doesn't matter. The structure itself is being applied to the center line, So as long as the center line of the beam is on the edge of or within a slab zone, it's fine. Next, we'll start defining the band beam and draw a wide beam over the top of it. So as we said before, the band beam is a thickened slab zone. How we define thickened slab zones, we have to create an area using geometry lines. So we can define band beams in a few different ways. The first one being to draw the band beam manually. So I've got my grid centers at 0.5 meters and I want to create a band beam of 1 meter width. So I press the slab button to draw a geometry line, and then I click here, right click end, to draw an area that will have an increased thickness of a width of 1 meter. So we can just double check the distance, 1 meter, hit escape, hit F5 to mesh. So the slab thickness by default is 200, and if we want to make this something deeper, for example 600, we change the thickness property. By using geometry lines, we've defined the thicker slab zone that will form our band beam. This can become a bit tedious, drawing geometry lines, moving them as we start playing around with different band beam widths, especially during the preliminary design stage. So we have another slightly faster way of drawing band beams. We use the beam tool basically to define the width of the band beam. So here I set the width to 1 meter, click the start and the end point. Then I select the beam, I go to edit and convert this selected beam to a geometry line. And based on the footprint of the yellow line beam that I've drawn, it's converted it to a geometry line. So because we drew a line beam, we modified the structure, we lost the mesh. I still have to generate the mesh again and then input a slab thickness here. Oh, it looks like it remembered it previously, but if I was doing it from scratch, I would have to input the slab thickness. So again, coloring by thickness, we can see it remembered the previous 600 mil thickness in this zone. So we've defined the band. If we were to analyze the slab now, it would just treat it as a thickened slab zone, so acting in two directions, and we wouldn't be able to design it as a beam. To design it as a beam, we have to draw a wide beam over the top of it. So the wide beam is here in the Home tab. We can draw it by pressing it, and at the moment it's set to define using 2 points. Or we could use the shortcut V. So with define using 2 points, just like the line beam, we define the wide beam by pressing its start point and its end point. So the width of 1 meter is suitable. We can modify the width if we want to. And like the line beam itself, we can manually drag and drop its start and its end points. So we'll change it back to 1. The other way that we can draw wide beams is to define using 3 points. So in this case, the 1 meter matched the default value of the wide beam. That was good. The other way is to define using 3 points. So what we do here is the first click and the second click define the beam's width, and the third click defines the wide beam's length. Now you may have noticed that as we were using the wide beam tool, we didn't actually lose any of the slab mesh. So just hitting Shift E to show mesh. We didn't lose the slab mesh because by drawing the wide beam, we haven't actually modified the structure. The wide beam is just an integration tool. The actual structure is the thickened slab zone and the geometry line. So again, if we wanted to modify the width of the structure itself, let's switch off the wide beam, we would have to move these geometry lines or change the thickness of the slab zone itself. Now let's switch back on the wide beams and let's have a look at some of the properties of the wide beam. So the X and Y coordinates, that's sort of the start and the end point, that's fairly straightforward. As mentioned previously, the width is the integration width. So basically this particular property will define the width of the beam for design purposes. And now we have another property here called integration width. So let's see what this does, and we'll set it to 1 to match the width of the wide beam itself. So this integration width is the width perpendicular to the length of the beam that the program will integrate over to get forces from. So that will become a bit clearer once I show the results, do the wide beam design. We'll just move this out of the way. We'll come back to the beam design window. But we can see the orange width here, and these dots, so they represent the width over which the forces are extracted from. So right now it's only 1 meter width. While we're here, we can also see that there are approximately there's some design points within each span of the wide beam. This is controlled by span subdivision. So if we wanted to increase this or decrease it, we would change the span subdivision property. But again, there's no point in doing this if you've got coarser mesh. If you want to put more points, ideally you should use finer mesh. Hence why we saw that warning coarse mesh message before. And as we saw from before, the program automatically picks up that there are columns nearby points at these points. That was indicated by the yellow line. Now what we'll do is we'll keep the width of the beam, the width of the wide beam 1 meter. We'll change the integration width to 8 meters, and we'll see what happens. So we hit wide beam again. And we hit OK, ignore this message. We'll put this to the side for now. We'll come back to that. So at points 1, 11 and 21, they're colored a different color, meaning that that's where the support is. And what we've done when we've set the integration width to 8 meters is from the center point, it will try to integrate a distance from 0 to 8 meters up here. So the point at the top of the model, basically that would be outside of the slab, so it clips it back to the nearest point within the slab. So basically from the center of the wide beam moving upwards, it's only integrated basically half the width of the beam, or 0.5 meters, but from the center going downwards, it's integrated the full 4 meters. So what we've done by setting the integration width at 8 meters is we have essentially increase the integration width from 1 meter to 4.5. Again, if there was a slab zone up here, it would integrate the full width. So in this case, we're choosing to take forces from basically half of the span. So we've seen how to define line beams, band beams, and draw wide beams, and modify the properties of the various elements. Before we design them, we'll start having a look at some of the other settings that will affect the design. So we'll hit escape to clear, and we'll go into input and material properties. So the bulk of the settings that affect the beam design are under the beam tab, but we'll come back to that. First, we'll look at where we define the concrete grade and basically the creep and shrinkage parameters. So this is covered in more detail in another video, but basically we've designed a slab concrete type we've used the default value of 32 MPa, and if we go to color by type, we can see that every slab zone has its type property set to 1, which is 32 MPa. Hence, both of these beams will have 32 MPa concrete. So if the concrete grade varies at various points along the beam, it will use whatever concrete grade is at that particular point. So basically what it's doing is it gets the concrete grade from that slab zone at the particular design point. So this happens for both line beams and band beams. If we wanted to make everything 40 MPa concrete, we would simply hit this button, input a label, input 40 MPa from the standard concrete grades, use the pre-filled values, hit OK, and then simply change the type property to 2. And design type, that will be covered in another video. So currently everything is set to 40 MPa, and our beams, both the line beam and the wide beam, will be designed with 40 MPa concrete. Going back to material properties, next we will have a look at where we get the creep and shrinkage values from. So as we saw before, they're automatically calculated for both the beams and the slab zones. So the program takes the thickness of the slab zone, the dimensions of the beam, calculates the creep and shrinkage based on some these predefined parameters. Ideally now, because we've changed the concrete grade, we should change our basic creep coefficient as well. We can also modify the design, shrinkage, strain, and creep coefficient variability if we want to. Or if we don't like the numbers for whatever reason the program is producing, we can put in our user-defined globals for slab zones and for beams. So in this case, we'll keep it all as automatically calculated by the software. So again, if we want to see them, we select the individual slab zone. Again, that's forming the structure of our band beam, and we can see them here. As we can see, they're not program modifiable. We'll go back to the material properties, and we'll have a quick look at the beam material properties. So it's broken up into strength and service. So this is basically for design for flexure, also deflection calculations, and for shear and for torsion. So most of these are self-explanatory. The yield stress of both the longitudinal bars, the ties, longitudinal bar diameter, tie diameter. We input the effective cover. We have a few other ones which need some explanation. So the compressive reinforcement as a percentage of tensile. Basically what this is when the beam is designed in the compressive zone, there may be no compressive steel. However, for the calculation of deflections, we assume the designer will be putting in some top steel, for example, in midspan. So we get you to put in some value that we will assume is in the compressive zone for the calculation of I effective for deflection calculations. Beam stiffness factor, so this is only applicable to line beams. This will be discussed in more detail in the next video, in the design considerations video. But basically what it is we artificially stiffen up the line beams. Why this is here is so that we have design results more in line with one-way beam theory. But again, discussed in more detail in the next video. Minimum strength as per the code. We've also got the option of using I gross for beams, so this is only for line beams. What this does is it forces the section to not crack. So if we were, why it's in here, if we want to design the slab with support of steel beams, we switch this on, calculate some equivalent properties of a rectangular uncracked concrete section to match our steel beam, and then we would design it as such. Maximum crack widths, we specify these values 0.2 to 0.4 millimeters as per AS 3600 2018. If this is switched off, we use the deem to comply approach. If this is switched on, we calculate crack widths directly to section 8 of AS 3600 2018. The majority of the shear and torsion parameters are self-evident. If we switch off include beam torsion, we force torsion to be 0 at each point. If we switch it on, we specify some torsional stiffness reduction factor of the beam itself, and here we have the torsion constant. So please refer to the manual to see where this particular equation comes from, as it is currently not mentioned in AS 3600 2018. One final thing to mention. Effective cover for this particular is input in this particular box is straightforward for line beams. This is just the value that it is. If we press this button, we can specify line beam depth and the effective cover per line beam. Currently everything is set to 44. However, the question is, what happens for the band beams? As we said previously, the band beam is just a thickened slab zone. And if we go to material properties, slab zone cover is set under the slab design type. Again, more information on this in another video. So what happens when we design a wide beam? When we design the wide beams, which cover is it using? The thing to remember is that the whatever cover is set here under beams, when we design the wide beam, will overwrite whatever cover is input in that slab zone. So currently only design type 1, which is every slab zone in this particular model. Hence every slab zone will have an effective cover of 32. However, as we've input an effective cover of 44 here, when we design this wide beam, effective cover of 44 will be used. So with the beams defined and settings input, we'll start having a look at how we extract the results and design the beams. So hitting F6 to run. We hit exit and we can see the beam results are available here. So the both beams and wide beams will be designed for the envelope bending moment. How we define that, this was outlined in another video, but we'll go through it quickly again, is under input load factors. It will be designed for whatever force has envelope tick next to it. So it'll be load combinations 1 and 2 in this case. So we'll hit cancel so we don't lose the results. To look at the results per case or combination, we go to results, we go to beam for example, and hit case combination. So we've got the beam design window here. As we can see, the section is empty, meaning that the section hasn't been designed in this case. And then we can toggle between moment, shear, and torsion for this particular beam. And it will display the results for whatever case or combination is set. To design the beam or wide beam, we select one of the two, in this case the wide beam, and hit wide beam. And we'll ignore this warning message, and the program designs the beam for the moment envelope. So we see a lot of stuff here on screen, and we'll go through it all in detail to see what each thing means. So in the beam design window, we have the section view, basically the longitudinal steel that's designed in that particular section. At the moment we don't show closed ties, but that doesn't necessarily mean that closed ties aren't needed. So at this particular point they are. We see the beam report and the section summary for the particular selected section, and we see the forces, so moment, shear, and torsion. So we can change the section that we plot by pressing the arrow buttons here, or we can select the values within the tables themselves. With the reports, we can double click on the report as well to pull up the report in text format. And we can also export the current table that we see either to text or to Excel. So currently we see the summary of the results, so just the key values. We can expand it to see detailed results, the properties of the beam that we defined previously, so the properties per point, as well as the detailed reinforcement. So we show a lot of information to basically give the user all of the values and give the user confidence that the software is doing what it should be doing. So we'll go back to results and we'll start having a look at the various forces that we can see. So we'll come back to bending moments. At the moment I've switched off all of these design detailed capacity options. So what we see now on screen is the M value, so the bending moment results of the moment envelope. So if we switch on detailed, what we see is always colored on screen. So generally the blue color for bending moment means in the top of the section, forces and calculations in the top of the section, and red is in the bottom. So note this M is not the final M star value, but we'll come back to bending moments in just a moment. Shear, as we change to it, we see the value colored on screen, and we also can see the equivalent shear force which considers both shear and torsion. If we go to torsion, same thing, we can see the torsion force, and if we switch on capacity, we can see the capacity of the section. If we go all the way to the right, the capacity of the section based on the calculated results. So notice as we switch on various things, the color of the table changes based on what's displayed on screen. So again, we can see our equivalent force and the capacity all displayed. So shear and torsion are fairly straightforward, not too much to display on screen. Bending moment is a little bit more complex. So let's zoom into some of these points. So as mentioned previously, with everything switched off, we only see the calculated envelope bending moment m. Phi MUO is simply the capacity. So based on the final longitudinal steel that's calculated, we see the capacity of the section. We can see the bars plotted in section as well. Switching on detailed, we see all of the various bending moments at a particular point. So let's go to this one and we can zoom in slightly. Pull this down by some amount so we can see in a bit more detail. We see a few different numbers displayed on screen. So we have the envelope bending moment of 120. We have this value MVT. What this is longitudinal force caused by shear and torsion calculated to section 8 converted to a bending moment. So that's what this value is here. And then M min is minimum bending moment as calculated to the code. Then finally, if we switch on design, the design bending moment is the largest of these three. So again, toggling design, we just see the detailed bending moments by themselves. Switching design back on, we see that the value m star is minimum moment in this case, and that's evident from the table as well. So the design bending moment m star is the basically is the biggest of all of these values. And the final checkbox we can switch on is the capacity, and if we zoom extents, we can see in this particular case the capacity is much bigger than any of the calculated bending moments. So we can't tell why this is straight away. We could either look at the report or we could start having a look at some of the reinforcement results. So before we investigate point number 2, very briefly, what we're looking at here when we look at the detailed reinforcement is in the red, any reinforcement or any calculations done in the bottom of the section, blue in the top, just like for the bending moments. The final values AB is the final value in the bottom of the section, AT the final value in the top. The postscript T means tensile, C means compressive, and this bottom top corresponds to bottom top. Obviously, we have a few other additional options here. So for the wide beams or band beams only, we have an option of user-defined reinforcement. This is not available for line beams, band beams only. At the moment, this is set to 0. If we wanted to, how we would input user-defined steel, this is covered in another video in more detail, is that for the design type property of this particular slab zone, we go to the design type table and start filling in values here. Because we've left these values blank, the program will assume there's no user-defined steel and keep that value 0. But that's all covered in more detail. Specifying design types, putting in user-defined steel is covered in more detail in a separate video. So if we go back to the beam itself, results, wide beams, it remembers the results from before. It doesn't have to integrate again. We go back to our detailed reinforcement. Yeah, so that was the user-defined steel. The additional things that we see here are minimum steel. So this, if we switch everything off, the details, just show the detail, this is the reinforcement needed, simply in millimeters squared, to resist this this value of basically the bigger of M or M min. So it needs approximately 1200 millimeters squared to resist this minimum moment of 273 kilonewtons per meter. This result here, AST_crack, this is reinforcement needed for crack control. Because we chose a larger bar size N24 and we have a wider beam, to satisfy minimum spacing requirements within the beam, we need 4 N24s, so this corresponds to 1800 millimeters squared per meter. So basically the final reinforcement, this final AB value, is being governed by crack control. And as this is much bigger than the minimum reinforcement needed, we have a much larger capacity. So this is where this very large phi MUO is coming from crack control. Maybe if we drop the bar size down, we might get a more efficient design. There's a few other things that we can see here in the reinforcement results. So we have this ASC_VT. So this is longitudinal steel, additional longitudinal steel for shear and torsion. So for any tensile forces caused by shear and torsion. So again, investigating point number 2, we see some value here, and it's not necessarily we probably don't need 1800 to resist this value of 212 kilonewtons per meter. Why we see the 1800 here is that we initially do the flexure calculations, so this segment of the graph. Then when we do the shear and torsion calculations, we just pass through this larger 1800 millimeters squared per meter. So what it's done, it's recognized that there is some larger longitudinal force which is converted to a moment, so some larger moment caused by shear and torsion. It checks to see if the existing design steel, in this case 1800, is sufficient. It is. It does its check and it's just filled in this value. So it will probably need a bit less than it's less than 273, so it will probably be less than 1176. But the internal logic within the software, we just pass through this 1800, hence why we see this value here. Now let's go to point number 15 and discuss something else of interest here. So if we look at the section, we see that we have the tensile steel in the bottom of the section, but we have some additional compressive steel. We see this compressive steel is something very small, so 106 millimeters squared per meter. Now let's investigate these results, see where this number is coming from. So as per section 2, section 15 needs the 4 bars in the bottom, 4 and 24s for crack control, so we have 1800. However, it has some additional force or longitudinal tensile force converted into a bending moment caused by shear and torsion. So we do the calculations to section 8 of AS 3600 and see how much additional steel we need. So for this bending moment, we have, or for this longitudinal force, the existing tensile steel from the crack control calculations is sufficient. However, this longitudinal force due to shear and torsion is causing a net tensile force in the compressive zone. So initially we had no steel up there, but to satisfy the equations of section 8 we had to put something small in the compressive zone. So why we see the number here, this was a calculation of the bottom of the section. It produced compressive steel which is in the top, so then this 106 is passed through to the top of the section. So that's where that number comes from. And one final point that we'll look at, which also has some seemingly strange results which we'll try to make sense of, is point number 14. At point number 14 we see a spike in the MVT value, which at 13 is not there. So if we look at the shear and the torsion, point numbers 13 and 14 are similar. Point number 14 has larger torsion, and the shear is a bit less in point number 14. If we look at the equivalent shear force, it's almost the same between the 2 points. So going back to the bending moments, it will be clear once we have a look at the detailed report in each section why these results are occurring. So let's open up point 14 and point 13. Reduce these and have a look at them side by side. So we scroll down to shear and torsion design. I see the report here is a little bit longer because it's done some design. So we can see that point number 14 on the right here, where there is the spike, has much larger torsion. And then if we scroll down a bit, looking back at 13, we go down further, we see that torsion reinforcement is not needed, so this torsion moment does not crack the section. Therefore, because the section isn't cracked, we can use we can essentially waive the minimum shear ties to AS 3600 2018. So essentially the section doesn't need ties. So if we go back to the results, we can see point number 13, we have no closed tie results here. Now looking at section number 14, we have a slightly larger torsional moment, which if we look here, it has caused the section to crack. Because the section is cracked, it's assumed that the concrete is ineffective for shear calculations. Hence we need some minimum shear reinforcement. So going back to the results, we see some legs 4 and 12s at 190 spacing at point number 14. Then going back to the reports, because we need some transverse ties, according to the requirements of clause 8.2.7 of AS 3600, we have to calculate additional longitudinal tension forces caused by shear. And hence we do that calculation and we get some value of additional longitudinal force, which we then convert into the moment. So hence why we see this spike here. So for point number 13, it was not necessary. We didn't need it. We didn't need any ties, hence we didn't have to calculate this force. We just made MVT the same as the envelope bending moment. However, for point number 14, we did need ties, hence why we see this spike here. So the purpose of just talking through these 2 points was just to show you, despite there being a lot of information on the screen, you can start stripping the information back, switching off the various types of results, flicking between the different types of outputs, including the detailed section summary, to see where the numbers are coming from. So summary of what we've covered in this video: we've discussed the difference between a line beam and a band beam and how we model that within the SLB software. We figured out how to input band beams and line beams in the program and edit their properties and what settings will affect the design. We've also had a look at how to design the beam, view the results, and query the results produced by the software. This concludes this video. Thank you for watching.